Good evening everyone. Welcome back to the fifth day of the Gyan course. We are now ready to begin lecture 10, which will be delivered by our esteemed international faculty member, Professor Sukumar Kamlasadan sir. We are truly honored to have you with us. We look forward to learning from your vast knowledge and experience. Please sir, the session is over to you. चार्जर लगाई नीचे Okay, again, good morning. So, were you able to do the integrated P&D power flow assignment yesterday? Yes. If you were able to do, raise your hands. Let's see, just to get the count, the number. Yes. Okay. You were okay. How many of you were able to do? Just raise your hands. Just not fully. I see. You were able to do. You could. Uh, so what we will do is we will probably spend time this after the lecture on that, and then I will show you the OPF part. I will again show one more time, and maybe I will give you a code so you can practice at home. So we won't focus much on that. So today what we will do is we will talk briefly about some advanced topic, and one interest which I gather from discussions with people here is the control of inverters. So I thought maybe I'll touch base a little bit related, but not exactly what we have in our curriculum, which are two different things. One is what we call it as a microgrid, to give you a concept and idea about what is a microgrid, and also we'll talk about how the control in the inverter happens. And the control in the inverter, there are some type of controls in the inverter called grid following, grid forming, those kinds of control, which is actually controlling inverters. Okay, not so. Now we have talked about the grid. We talked about how the grid can be managed. We talked about how the power at a higher level can be reference power can be given to the inverters, right? Now, how the inverter control happens is something that I thought I will talk today. related to microgrid and how the secondary tertiary control signals can transfer. This is a area in itself, meaning this needs more understanding, but at least I will introduce. It's not a 1 hour lecture topic. It needs more understanding. If you are interested, if you have some need with respect to research or some, I can give you some additional documents. Okay. So that's the plan, and that actually and that can be applied in real time, in working on real time. So it's related to what we are talking about in advanced topic and real time. So with that being said, so I will take the first hour to talk about this, and then we will move on with our completing the TND simulation and one small example for optimal power. So that will be our agenda. So when you control an inverter, the inverter is basically what we call it as a front end of a inverter based resource. Okay, what do you mean by front end? Meaning inverter is the one which connects the inverter based resource to the grid. Okay, inverter based resources is not inverter, right? It is actually the resource, and it could be, for example, battery, it could be photovoltaic, it could be any other devices that's connected behind the inverter. So what we will do is we will be talking about not the resource. Okay, how to model a PV farm, how to model a wind farm, and how to model a battery, we will not touch. We will not talk about that. That also is important, but that we are not working on it because we wanted to talk about inverter connections, inverter based resource. So when you look at the inverter based resource, the inverter is the one that is facing the electric grid, and this inverter has a DC side input. Okay, this DC side input on an inverter actually has power, like a PV farm, wind farm, whatever power is connected. And after, when the power is connected to the DC side of the inverter, the voltage on the inverter, when the power is changing, voltage on the inverter on the DC side changes. Okay, now you already understood the relation between power and voltage, right? If you push the power, wherever you push the power, voltage goes high. If you absorb the power, wherever you take the power, the voltage goes low. So active power is directly related to voltage change at the terminal, right? And it changes when it pushes other places too. So at the DC side of the inverter, where the power sources are connected, when the power sources pushes the power or takes the power, the voltage on that side wobbles. When that voltage wobbles, on the AC side voltage also wobbles. So the first thing, if you are going to look at an inverter, when you design an inverter or construct an inverter, is to make sure that the DC side is stable, is not wobbling. So the AC side is not wobbling. So inverter manufacturer does that in a simple way by connecting a capacitor on the DC side. Okay, so if you connect a capacitor on the DC side, when the voltage wobbles, capacitor will sit like a shock absorber, right? It just absorb the voltage and then balance the dynamics of the voltage. Capacitor is not able to deliver a power. It's not a voltage source. It is a dependent voltage source, meaning it has to be dependent on something else. So that capacitor will change its storing values for the voltage and then balance the voltage. Okay, so that's basically on the DC. So when we are working on an inverter connected to an electric grid, studying some work on the inverter, there are two ways you can study. One, you study by saying that the DC side is stable and only work on the AC side. So after work on the AC side, meaning what are the things that you should work on the AC side, I'll talk about it in a little bit. Or you could say, well, DC is not stable, photovoltaics comes or some, then what will be the effect on the AC? So it's not an or, it can be first step and second step. First step you make DC stable and then talk about it. So to work on, say, DC is not stable and what is the effect on the AC side? To work on that, you need to have DC side modeled, meaning you need to model the PV farm, you need to model the wind farm, whatever, and then you need to find out the change on the DC side appropriately. Then only work on it. That's why I was telling, somebody was asking, I think we were discussing what type of tool you use, what type of software we use, how do you model? It depends on what you want to do, right? So if somebody do DC side dynamics and check on the AC and then work on the electric grid, and then you put a voltage source on the DC side, then you say, I mean, this model is not good. The model is not complete, right? You cannot study like that. You understand, right? If you are working on the AC side related aspects, we can make the DC side constant or DC side with the capacitor and study the AC side. So that's basically the DC. So in all the work that we are talking today, now the discussions we are talking today, we are not talking about the DC side. Okay, we are not talking about how the wind farms are modeled, PV farms are modeled. It's a lot. I mean, of course, you can study that and separately. Now you look at what is on the AC side. So AC side and the inverter, normally inverters are called, normally inverters which are connected to electric grid and managed working with electric grid are three-phase inverters. So because they are three-phase inverters, it will be generating three waveforms as output, and those waveforms are voltage waveforms. So the inverters that we are connecting or working on are generally called voltage source inverters, meaning the source of the inverter, at the source side of the inverter, it works as a voltage source inverter. Right? Not many energy sources are voltage source. So for example, photovoltaics. Photovoltaics are not considered as a voltage source because it is a current source. It is pushing current to the electric grid, and that the current has infinite capacity from, actually even not a current source, but ideally we say current has infinite capacity and pushes the power. So it's controlling the power, it's called current. But if you are in, like, for example, working as a battery, and then you will consider that as a voltage source. Okay. So the topology or whatever we discussed is on the as a voltage source. So some basics. So these three lines that you see is a three output or three-phase output that comes from a inverter. Okay. Now the next part is an operation of the inverter. How many of you have heard about a operation of the inverter? Inside the inverter, how the switches are configured, just like in a conventional H-bridge inverter, or switches are configured, how the PWM signal is there, how the inverter PWM signal goes to the inverter, and then inverter is controlled. How many of you have understood or read that? If you can raise hands. Some have got the idea. So that is basically what is the fundamentals of inverters or fundamentals of inverter-based operation based on power electronics. So it's a power electronics one. With the time that we have today, it will be hard for me to discuss that basics or the fundamental too. Ideally, what happens is the voltage is generated from the inverter based on the operation of the switches. Switches are power electronic switches or electronic switches that moves very fast. Because the switches moves very fast and the switch combinations that happens, the DC input that is coming in will be changed in the form of a step change of DC on the positive side and step change of DC on the negative side. This is the how, and so how fast you operate the inverter, how you do that. There is some ways to using what we call it sine PWM signal. So you have a reference sine wave. There's a method there. That method finally gives you a step change of the positive sine wave and negative. That's what it does. After that, it passes through a filter and it cleans that step change into a good, closely good sine wave. That's basically what the inverter does. So having said that, the inverter has switches inside this, or electronic switches, and that switches are controlled by PWM, pulse width modulation, or sine PWM, sine pulse width modulation. And there are 6 such switches, 3 on the positive side and 3 on the negative side. So those 6 switches you are controlling utilizing 6 pulses that goes to the inverter, and these 6 switch pulses are derived from a 3 voltage signals. Okay, so these voltages are changing. Okay, so they are called voltage controlled, meaning these voltages what is coming out from here, which is going to this pulse width, are changing. Based on that changes in the voltage, it generates pulses, different pulses. Okay. Now, what the change of voltage happened? That change of voltage, why it is happening? It is happening because of the control of the inverter connected to the grid. So that voltage change happens, it changes the pulses, and then the output changes, and then output will pass through a filter. So in this case, it is a L inductor and a capacitor, and LC. So that filter is called LC type of filter. So is that the only way you connect a filter? No, you can collect the filter just as a L, just an inductor. Okay? You can also connect the filter LCL. Right? You can do several different combinations of filters. So that filter is actually not a part of the inverter. Filter is actually to clean the power output going out from the inverter. So good so far. So that filter output that goes out of the inverter goes to the electric grid, and the bus that is connected to the electric grid from the inverter, and that bus is known as PCC, or point of common coupling, or point of common connection. There are 2 different ways that use. This is not an interconnection point. It is a point of common connection. Point of interconnection is something else, not this. So you may see also some people saying POI, point of in. That's not. That's a collection of the inverter that's connected. So that point of interconnection, point of common coupling voltage goes to the electric grid, and you can represent. There will be maybe a load connected to it, and you can represent the electric grid lines and the electric grid as a voltage source connected, or you can represent the entire electric grid here. What electric grid we are talking? For example, IEEE 123 bus system distribution network. Remember we talked about, you can connect that to one specific point. So if you look at a one point where we said a red circle and say inverter DER and pushing the voltage, remember that circle is basically this whole. So at that time we talked about details of electric grid, and then we said circle, and we talked about how you manage. Now we are talking about details of that circle, and no electric grid there. We are just trying to, ideally what happens in real life, details of this whole thing and the whole electric grid, everything together will be working. Good? Make sense? Right? That's the inverter connection. Now what we are focusing, so we have 2 parts. We can focus here, we can focus the inverter, right, and we can focus the grid. Rather 3 parts. But what we are focusing is how the control happens on the inverter and when it's connected to the electric grid. Okay. So there are 4 parts that you can focus. So you divide into small 4 pieces, and so you understand why, what we do and why we do that. Good. So the control of an inverter is actually done through calculating the output voltages and the current. So you see the current, the voltage here is tapped, and the current here is tapped. Okay. How do you tap the voltage and current? You tap the voltage and current by connecting some sensors, and then you measure the voltages and current and you take it, and then you clean that voltages and current that you are tapping to reduce the noises by putting some filters there on those sensing, like for example low pass filters or filter combination. So when you take that, you will be taking how many voltages? 3 voltages. You will be taking how many currents? 3 currents, because it's a 3 phase. So you have 3 voltages, you take 3 currents, and you see 3 lines there. It takes 3 voltages and 3 currents. Okay. Good. Okay. So after you take these voltages and currents, what will you do? You will control the inverter. To control the inverter, you don't want to control 3 controllers like A phase, B phase, C phase, and 3 controllers connected together. It's too much. So you try to assume that the inverter output is balanced on a 3-phase inverter, and then control only the inverter output using 2 controllers. Okay. So now you take the knowledge from synchronous generator. If you want to control a synchronous generator, 3-phase synchronous generator, you take the 3-phase, but 3-phase is balanced. You take only 2 out of 3 by transforming from 3-phase to 2-phase. And that transformation of 3-phase to 2-phase, I think we discussed this in some time. Transformation of 3-phase to D-phase, 3-phase to 2-phase to control is called DQ transformation, where you take a 3-phase ABC, convert that into a coordinate called alpha beta. From the alpha beta, convert that into coordinate called DQ. Okay. Basically, the bottom line is you are trying to stand on one phase, and you look at other 2 phases. So you see only 2 moving, because the third one you are standing in it, right? And if you stand on it, the other 2 moving, and the change in those movement with those 2, you consider that as a change in the phase reference. So if you do a forward backward sweep, you get 0 degree, 120 degree, 240 degree. Right? That is a phaser of the 3-phase. That's not the change. That's staying like that. What you do then is you look at 0 degree and see if there is anything which is like wobbling ahead of 0 degree. Okay, that's we call it delta. Okay, so that is a change that you. So when you say V angle delta, V angle 3 degree or 0.4 degree. That 3 degree and 0.4 degree is not 120 to 40. Is not that 3-phase shift. It is a change from that, right? That is basically the delta. So you look at that delta. So I stand there. When I look at the other 2, it's 240 and 120. I see they are in 240 and 120. They are same, like as if 2 cars going on the same speed, and you are in the middle. That car and this car is at the same distance. You will see as if they are stationary, right? If they start moving, then only you will feel, oh, they are moving. That is basically what you call it as a delta. So what you need is that delta. You don't need, if they are stationary, you don't need to do anything. You can all move in the same way. But if I want to control all of them, I need that change, that delta. Following? So that is done through converting from ABC to DQ. So if you convert from ABC to DQ, when you transform from ABC to DQ and control, you will be able to do the transform from ABC to DQ, but you need this delta. You see, that is the only way you can convert from this delta or theta. You get it from looking at how the grid is operating. Okay. So for example, if the grid frequency is 59.9 and the grid frequency would have been ideally 60. So you say that, well, the delta the grid is operating is 2 degree or 3 degree or something. So frequency is slightly different, not in the fundamental form. And you take that, you want to get that number from the grid. And if you get that number from the grid, then I can operate the inverter, and I can operate the inverter and connect it to the grid. What happens if there is no grid? What happens if the 60 degree is not there? So then I will stand there and say, well, I don't want to get it, I'll make it. You see? Because there is no grid, right? If it is somebody there, and if I want to work with that person and move along with that person, I need to know how you are moving, what is the change in it. So I will catch you with that change, and then I will move along with you. You see that? So this process of gathering the delta or theta, there are 2 parts. One part is I need to first know whether the grid is there or not. So I can decide whether I should move with you or I should not move with you. That's first part. Second part, if it is there, I have to get that theta. Because I only get frequency, right? I don't get the theta. I have to get the theta out of, or the delta out of that frequency. So there are two parts. Is that clear? The first part is whether I'm connected or not. Second part is I need to get it. Let's assume I'm connected. Okay, that means I need to get the theta or delta. So what you do is you take the voltages of the connected part voltage. So when it is connected, this voltage, if you take, I know that voltage value, right? Take that voltage and then get the theta out of that voltage. Getting the theta out of that voltage when it is connected is done through a box called PLL. PLL full form is phase lock loop. Okay, and this PLL, how many of you heard of phase lock loop? You've done, yeah. So the phase lock loop is actually not fundamentally done in electric power engineering. It is done in communication systems. What it is, why is it used for? It is used for to send a signal and lock a signal with the help of, with respect to an oscillation. So for example, if there is an oscillation signal, we lock this. So that's a concept. So that concept you borrow. And how do you do the phase lock loop? How the phase lock loop works, I will show you in a some. It is like a controller, small controller, to tap that. Why do you need a controller there? There is a reason for also. So 59.9, I am getting that angle and I am taking, right? Is this 59.9 of the electric grid stable? Always 59 point? No. So I am moving, electric grid is moving. So I am taking from the electric grid. And I have to keep on taking from the electric grid because the electric grid is moving. You see? That's why we need a controller to adjust it. Are you following conceptually what is happening? So that is what we call it as a PLL. So then you can convert from ABC to DQ, and then you are able to design controllers. Good. Now what controllers we design? Well, you design controls to push the power that is set by the electric grid. So for example, if the electric grid say, hey, I need 30 megawatt, I have to push the 30 megawatt to the output. I think the same one. Yeah. Turn it off. I guess. If they are too bothered, then. So. Yeah. It's actually either you need to curtail or you need to reduce. We don't have a knowledge on how to reduce. So what we are doing is curtail. You remember curtail, right? So that's the same thing what is happening here. So so where am I now? So this is one other thing which I say always when the distraction can I drift. Yeah. So the power that is given if there is a grid, I am always saying that I need this reference power. That reference power, whatever is grid is saying, I need to supply. Right. So I take this reference power from I take the power and then I look at the reference power and then I wanted to supply that. So to look at the reference power and make the get the error and then control, you need the actual power. How do you get the actual power? Again, the same current and voltage I tap and I calculate my power. Can I calculate the power from current and voltage? Yeah, we already did it. Power flow. We have the equations on how to calculate the power from current and voltage. VI sin theta or VI cos theta and 3 times whatever that is, right? So you know how to calculate. So you calculate the power, it's power calculation. You look at what the power is given by the electric grid, and then I try to reduce that error. So the power error, when I reduce this, I have a problem. How do I reduce this power error? Power is based on current and voltage. Is that power related to current or related to voltage? Right? So you have to first assume that the voltage is not changing and then say that the power is related to current, right? And that reference that you are converting from power to current is through this PI and you deliver the reference current to the controller from output of the controller. So if I am injecting the current to the inverter, right, and converting getting a sine waveform, then no problem. I can take that current, convert into sine wave, I'm done. Okay. But if I am converting generating the signal using voltage waveform, then I have a job. I have to convert that current signal to a voltage signal, right? Or the voltage is also changing, then I have to convert the current and then look at the error in the voltage and then control it. Okay. So if the voltage is not changing, very stable, I just need the power converted to current and then I control my inverter now. But if the current and voltage is changing, I just need to take the current change, then I will have to take the voltage change, and then you apply to the inverter. So if you have two of them changing, you have two controllers which has to work together to control the inverter. Okay. So if you have two converters working together to control the same objective, such control architectures are called cascaded controllers. Okay, cascaded operation, which means both of them are connected together to work on the output. So here you will see that the current is generator, you have input reference that goes to another, based on the current input right here, that goes to another PI and then generate the voltage signals out of it. So you have one controller here, another controller here. These two controllers work together to convert the power to current to voltage, and then you power to voltage and voltage to current. I'm sorry. Then you give the inductor the output value for the voltage, right? So that is called cascaded operation. Anytime you don't have to have this cascaded operation. Depending upon what you are going to control, you can simplify. But if you have this cascaded loop or two loops there, it's safe that you will be able to control. It will be maybe complex, but it's safe that you can control. Do you understand? So what are the three pieces? or so you need to generate the angle or calculate the angle, right? And you also need to have a voltage, right? A good voltage, whether connected to the grid. If there is not connected to the grid, you need to calculate that voltage or get the voltage. Good. So this is a grid following modes of operation. You connect from the PCC, get that. Are you comfortable with this picture? Because I'll move after we understand this. I'll move a little fast to cover some of the things which is here. So the grid following mode is basically like this. Now grid following mode, you can say that it has got a voltage and current, a power reference given by from the grid, and then you follow the power reference based on the angle you calculate. Such a grid following operation of the inverter, mainly the inverter's job is to push the power. So the inverter can be generally considered as a current source model or current source representation where inverters can push the power. So as opposed to grid following mode of inverter, for a grid forming mode of inverter, you generate the angle. Okay. Oh, you understood, right? You generate the angle. Oh, you also need to generate the voltage, right? Because you don't have if grid is gone, you don't have a voltage. Or generate a voltage means what? You need to maintain the voltage, right? So if nothing to maintain that voltage, nothing is connected, this voltage start collapsing if you don't have a voltage there. So you have a reference and you maintain the voltage. Okay. So this two number, which is angle and the voltage, has to go to the controller, and then you have this loop, and then you control. Right. So what's the difference? Difference is I know that I can generate the angle from PLL. How do I generate the voltage magnitude and voltage angle if it is not connected to the grid? Okay, and there are some techniques. Okay, one technique to generate these two is by looking at the actual power and the reference power and then generating voltages and angle. Also, you may ask the question, oh yes, we did look at actual power and reference power before too. But that we did not generate voltage and angle. You know what we did? We took the delta. That's okay. I'll put it because I'm more comfortable in putting. So if you were to again, where am I? Oh, yeah. So if you were to get the synchronous generator output from the inverter, no synchronous generator real life, we call it VSG or virtual synchronous generator. You are virtually creating. And if you try to generate the virtual, when you do virtual synchronous generator, what is virtual? What is there? It's a bunch of equations. There is nothing other than that. Well, you generate voltages and everything from the inverter using bunch of equations. That's why it's called virtual. So can you write the equations for the entire synchronous generator? Yeah, you can. What equations you write? Well, you look at a synchronous generator model. The primary fundamental equation for a synchronous generator, what you can represent is two derivatives, first order derivatives, or one second order derivative model of a synchronous generator. Have you heard of second order derivative model of a synchronous generator? Fundamental? No? This is an undergrad. So if you say no, that means you are going backwards. So if you are working on a research problem, the two second order two equations that is very fundamental for a generator is known as swing equation. Have you heard of swing equation? Okay. So swing equation, why it is a second order? Because it's there d delta divided by dt or d theta divided by dt, derivative of the angle is equal to angular velocity omega, and derivative of that omega, d omega divided by dt is Pm minus Pe 1 divided by 2hs, where h is representing inertia, Pm is representing the mechanical power, Pe is representing the electrical power. That electrical power can be written in the form of V1, V2, Y12 cosine delta 1 minus delta 2 minus theta. Where did we see this equation? In power flow. So you can put that equation there for the PE, then you can have a PM, you can connect the PM and the PE as the swing equation, then you have a synchronous generator model. So if you have a synchronous generator model, right here, d theta divided by dt is equal to omega, d omega by dt is Pm, P reference Pm, minus Pe, minus you can also include damping of this delta omega divided by omega. This is a synchronous generator swing equation model. That synchronous generator swing equation model can be included in this like a map, just a map. So if you do that, is this power you know? Well, your power you know. That's coming from the output of the inverter. That power you know. What about this? It's a number. What about this? Well, that you can tap from the delta. This is a number, right? So these two numbers are, you can place it there and you can generate this equation right here and then generate this angle and the voltage. This is what we know as still virtual synchronous generator. One form of virtual synchronous generator called swing equation form of virtual synchronous generator. So just only swing equation you are considering, only the mechanical part. Is a governor there in this model? No governor. Can you include the governor here? Yes, you can. That equation right here, you see, you can actually extend this equation to provide the governor equation. If you provide the governor equation, you will get one more derivative. We add the derivative here. So one derivative for the swing equation, one derivative for the governor. So if these two derivatives are included, then your governor equation is also included. All equations, by the way, there is no real generator. So the governor equation you can add. So two equations you can add. So then it will become third order, right? The third order swing equation emulation of swing equation. So you can actually use this algorithm and change the algorithm E and theta based on J, which is called inertia. No real J, that is now become inertia emulation. You are emulating inertia much like a synchronous generator. Oh, can you also change D, damping? Yeah, you can introduce damping much like a synchronous generator and utilize the damping and put the damping coefficient much like a synchronous. The use of, if you use this and try to generate the inertia for a frequency, this is called inertia emulation. Okay. So that inertia emulation is basically to get some value of inertia when you have inverter connected. You understand the fundament? Yes. So it works a little differently. This there it stores. So in a metal, it stores the kinetic energy, right? At the end of the day, what happens? That stored kinetic energy is pushed to the system, and that stored kinetic energy is working on this speed. So at the end, what happens is the stored kinetic energy is making that change in the speed in a different way because of the stored kinetic energy. It means it stores the energy and then releases energy after some time, right? That's what the metal does. It stores energy, releases energy after some time. So that stored energy you are releasing after some time, right? Similarly, this J also, instead of not storing the energy, this J will change the derivative shape different. So what is, end of the day, what is that shape change happens? That shape change is happening for this power. So the power output coming from the inverter or power output from the generator will be going to the reference point, but it will be taking a different route. Instead of going this way, it goes in a different, some other. If it goes a different route, the frequency, when it frequency dips, it will dip in a different way. It will not dip like this, or it will dip like that. So even though you don't have a storage, that's energy stored in a shaft, rotating mass, the end results, it's actually taking the power route in a different way. You understand? Because, oh, by the way, I mean, you need a prime mover. So prime mover is right there. So we are assuming that we have some energy storage, from batteries. None of these things are going to, see this active power push cannot work without a active power source. That active power source, there are two ways, like PV farm or the battery. Active power source from the PV farm also works. It has to be dispatchable. Remember, we are emulating synchronous generator. So as long as you have a source that is dispatchable or close to dispatchable, so in the inverter world, the only way you can make a dispatchable source is by connecting energy storage or some other device, right? Just photovoltaics is not. Remember the story about dispatchability. So it is not. It is still called emulation because you are not. So you need another thing. You need size, inverter capacity. You need to have a larger inverter. So all those things are known. So how large is large you need? How much source that you need to emulate this J? How much frequency lift that you get from 3 inverter, 2 inverter, 4 inverter? What is that? So those things are all open research questions. Nobody knows. Only some experimental studies done in, like I said, some places people have studied something. So all these are open-ended questions. We don't have answer to those questions. However, the answer what we have so far is we can emulate. And that's why this problem is very attractive, very nice to work on. And what is the magic number? How many inverters on a system will make this inertia good? And it depends on the electric grid. Like I said, in a long grid, in a transmission distribution system. So those things are all unknown, and those things are all not known. So this is one way. Oh, now you may ask the question: Can I model a excitation system? This we said swing equation. The two model. So if you go to the second order differential equation for the synchronous generator, we call it swing equation. It's two swing equations. If you go to the higher order, I don't know whether you have seen this generator model. If you look at you can look at in Simulink. Generator model is there up to 8th order. It's called 8th order model of the generator. Is the largest generator model that we have. So 8th order means how does the order goes up? Order goes up depending upon the differential equation which you have. So one way to emulate the synchronous generator is go up to all the way to 8th order. So you write 8 differential equation in this math form and then control the inverter? Yes, you can. If you are tasked to do, you can do that. So there is a funny thing in the control system where you say that too many knobs are also complex. So if you need to have few knobs, then it's better, but more knobs are complex. Knobs means, so let's assume you are controlling now, you have J, you have D, these are knobs, right? So you have to understand what is the trade-off with respect to the. So this, what it does is emulating some kind of a excitation system. Now we already talked about excitation system in a generator is coming from the flux, right? Mechanical power converted into magnetic power, from the magnetic power converting back into the electrical power. That is a synchronous generator. What is there in the inverter? No flux. You don't have anything like a flux concept there. So how do you generate the voltage? Well, you generate the voltage from reactive power. And what is the reactive power? It's the difference between the current waveform and the voltage waveform. So that reactive power emulation you can do as a concept here by looking at the voltage at the nominal value, PCC value, add that to the reactive power reference. So this is a voltage reactive power combination. And then utilizing that's like a constant, a time constant, and say that as a E. So in the excitation model for a synchronous generator, there are different ways of excitation. You have a reactive power excitation, you have a voltage based excitation, you have a reactive power voltage combination of excitation system. All those excitation models you can represent in here to generate the voltage. So fundamentally, in a farming architecture, you will need this angle and you will need this voltage because you don't have an electric grid connected. So at this point of the inverter, we should have a voltage and we should have an angle made by the inverter itself. So such inverters are called farming. So let us recap one more time. So if we have an inverter, we said that inverter we are considering for inverter based resource or three-phase inverters. We are not going inside the topology of the inverter and see what the inverter topology changes looks like. We just generally consider a three-phase inverter with 6 switches controlled by pulse width modulation technique for the 6 switches, sine PWM technique. If you take an inverter like that, the output of the inverter will be 3 voltages and currents coming out from the inverter. DC side of the inverter, we assume there is a DC source connected, which could be battery, photovoltaic and all. Modeling of the DC source, we kind of conveniently ignore and we say that DC source will be there and it will provide the voltage. And you are considering a voltage source combination, as if you consider like that, to control the inverter, we need the voltages and the currents connected to the point of common coupling. That inverter, when you control the inverter utilizing 3 different control loops. One control loop is calculating the power, finding the difference in power, how much power I need to push to the electric grid. Remember that we said the reactive power is this much I need, active power is this when the grid is present, right? and that change in the power you pass through a controller to deliver the output of that controller in terms of voltage. Then from there you take this output to control a reference signal for the sine PWM, and that voltage signal goes to the inverter. This is the control architecture. This control architecture, right now you will see there is error here, there is error here, there is error here. So we say that there is one loop here, second loop here, three loop here. So this is a three loop control architecture. All of them working together. Such control architecture we call it cascaded control architecture. Three loop cascaded. To make sure that they don't fight with each other, all the three loops you divide by time. We call it time scale separation. One will be faster, one will be slower, the second will be more slower. Fastest will be the innermost loop which is connected to the inverter. The next will be the next fastest, and then will be the on opposed to frequency side. The innermost will have more frequency range called wider band. Next will be next band, and the third will be smaller band. So this is how the inverters are controlled. To control that inverter, we change from the ABC 3-phase to DQ because we say it is balanced. To change from ABC to DQ, you will need the angle to lock on. That angle you borrow from electric grid because electric grid is sitting there. Looking at the frequency of the electric grid, setting the angle. To get that angle, you use a box called phase lock loop, which is basically to generate that. This is how the inverter operates when it is connected to electric grid. When the electric grid is not there, we have challenge. You need to generate this angle by ourselves. That angle is not coming from the electric grid. Oh, we have another challenge. This voltage which is there, which is stabilized by the electric grid, will start going down. So you need to lift that voltage magnitude to a constant value and also generate our own angle. Such inverters who does that job of getting the voltage and angle are called grid forming inverters. The one which is getting the angle from the electric grid and then doing its job are called grid following inverter. Same inverter can do grid forming and following. So then we will say, hey, my inverter has two modes of operation. One is in grid forming mode of operation, second is grid following mode. So this is how you do grid following. To do the grid forming, you can generate these voltages and angle. One way of generating the voltages and angle is to looking at how the voltage and angle is generated using synchronous generator and writing down the synchronous generator equation, all math, no real machine, no real spinning mass. Using mathematical approach, you can generate like a voltage and angle using synchronous generator, and that process is called virtual synchronous generator. And whatever you generate for the synchronous generator, for example, inertia you generate, that's called virtual inertia. Virtual damping. You add virtual to everything and then it will become. Will it work? Yes, it works. How much of it works? How much it will not work? How you have to change the number? How much you have to change the number? That is, people still work on it. So this is an area that you can also contribute and work on, see how many inverters are required and how you need to control and things like that. Yeah, we are actually out of time. You were wanting to do some models. Yes. Yeah. Yes. Yeah. You need a storage map. Good. You got the fundamental idea here. We cannot discuss all of them, essence of time, but at least you should know what is this, what we are doing. I always talk about why, what. How is you can think about how, but understood, right? So far, another way you can do, don't worry about synchronous generator, modeling virtual synchronous generator. Like too much, lot of stuff to do to synchronous generator. Then I look at how the synchronous generator can be modeled very easily. Well, you model the synchronous generator performance very easily on what we call it as a droop behavior. A droop means when the frequency changes, what I need to do is to push the active power. I don't care about angle and other things. Oh, I change the frequency, push some power, and maintain the frequency. Voltage changes, I push some reactive power, maintain the reactive voltage. Why do I need to write all the equations? So you take a lookup table, make a graph, and you say that frequency going down, push power, more power. Negative, positive, so negative slope. So make a slope. Put the slope in linear operating region. Forget about all these elements. That what a type of generating voltage and angle is called droop control. Droop control algorithm. Droop control algorithms are implemented in real life and it's been done by inverter manufacturers. Pretty easy to do. It cannot generate any inertia. Well, it supports the frequency dip. Nobody know whether it is inertia. So when you do the frequency, you would know this story about frequency change. I want to go too far in here, but this frequency. This is your frequency regulation graph. Everybody probably have seen that. This when the frequency like a 50 hertz with respect to time, or here there is enough. See that when the load changes, frequency drop. This part of the frequency is based on the inertia. Here the governor will act, call it primary. Here AGC LDC will act, call it secondary. So this is how it transits with respect to time. This can be around maybe 4 to 5 seconds up to 2 to 10 minutes and greater than that. This is how the frequency wobbles in general in an interconnected system with many generators working, many generators. So here you have each generator governor with droop will act. Okay? So this is what we generally call it as inertial response. And this we call it primary frequency response. This is called secondary. Okay? Now, if you are connecting energy storage or a battery, and this part is fast frequency response. This is without the inertia emulation. If you connect the battery, if you connect push the power from the battery fast, you can still get to improve. Oh, and this is known as frequency nadir, the lowest point. So that frequency nadir, you want to make sure that it will not go below 49.55 because you'll have under frequency cutoff. So you want to maintain the frequency within that limit. Now the inertia emulation or inertia improvement happens this whatever inertia, and this rate This is called, I'm making this a little bit messier now. So this is generally called Rokoff, rate of change of frequency. So this is basically the how fast the frequency goes down, you know. So if this rate you control, you can control this point. You know, if the rate is faster, then it goes down. If the rate you try to make it slow, then this is, so this point control is not just putting some flywheel or inertia. This point control, emulated inertia. This point control is also related to how fast an I change. So if you connect a battery energy storage here, this one is going to this now. So it's already started lifting. That one is why it says that it goes all the way here. You see? So this is because this ramp has improved, not because this is doing inertia response. It is because it is actually, this slope is now becoming, maybe another color or something. I don't know how. Anyway, so this slope is like this now, you see. So if you are looking at this line, it's the battery line. That slope is now becoming this. So because of that slope, it's lifting up, because of the battery. So that's what we call it generally fast frequency response. So there is something in the new literature, fast frequency response, which is generated obviously by battery. No virtual inertia. So this is like a frequency sketch in how you define frequency, how you work on frequency, how we improve the frequency. Each of those part what we are talking here are little different. This J is not going to necessarily work on the rate of change. It is working on coefficient of the rate of change, which means it is little different rather than just changing the rate. But the battery, power is changing the rate. So what I was talking here, So what I was talking here, this is a frequency response, right? So I can do a curve that talks about omega linear curve for delta omega versus delta t. This is called droop. P omega droop. Oh, will that affect that? Yeah, it will affect the frequency response because you are actually trying to change the power coming from the inverter to improve the power or reduce. Okay, so this whole box it can be designed. Well, I'll give you a sketch. Let's see. This whole box. See this box here can be designed by this many people. This many type of work is done in the literature, or maybe more. I don't know. This box is generally designed in two forms. One is called droop. Second is synchronous generator. And there is a third type borrowed from communication folks called oscillator principles. So virtual oscillators. So you can create oscillator. So for example, the inverter output you say, okay, yeah, I create it's like a sinusoidal oscillator. So you put oscillator without damping. It follows like a periodic waveform without damping, it follows like oscillator. So that oscillator frequency I control to 60 Hz per hour. So I have an oscillator output which is called virtual oscillator. And then I use control for the virtual oscillator. Forget about all the generators. So there are three different buckets of work done by people. One is going in this, which you call it droop. Second is going in generator, called synchronous generator. Third one is going on the virtual synchronous operator. So I may have so these references I can provide with you maybe if you wanted to talk about looking at it. So, but at the end of the day, what is the goal? To get the voltage and get the angle and try to behave this inverter operate much like a synchronous generator, which makes the system stable. That's the whole goal. So somebody was asking this question. I think you were asking, or somebody was asking this question. What happens if you have 100% inverter based resource? You were asking that. So if you have 100% inverter based resources, what I need is voltage and angle, right? For the inverter to work. So I don't care about frequency. Why do I care about frequency? Nobody is operating in speed. Nobody is generating frequency. Well, at the end of the day, maybe if I want to connect a device at home which is AC power, I may need a 50 hertz in the outlet. It's a different thing. So I work on the angle, generate angle. Then I take derivative of the angle and call that as frequency. Now the frequency is not so it is not global. Now it's local. The angles are controlled local frequency. I'm not saying that we will go there because 100% inverter based resources are not generally going to happen, because we worry not about inverter based resources, we worry about renewable energy. So renewable energy can be coming from hydropower. So nowhere in the world you will have a 100% inverter based resources, because as soon as the renewable energy mandate is achieved or the sustainability mandate is achieved, we stop right there. And sustainability mandates can be achieved with hydro. And we will be living with hydro power plants throughout our life. There is not like generations to come, because we have resources, natural resources. So having said that, will you get rid of synchronous generators? No, they're going to be there. So one comes from frequency, then go to angle. The other comes from angle, then go to frequency. Both of them has to coexist. There is no situation happens. I personally feel, I don't know, there may be school of thought, people may be talking different things. I don't think realistically you will have a situation in which you either work with angle or frequency. You have to work with both, and both has to coexist. Both have, so you'll have inertia less system, but I don't think you'll have inertia zero system, because these hydropower plants are there. Of course, small nuclear is also coming, I guess. So small nuclear is going to be there. Forget about gas and coal and gas. You can say it's all gone. Maybe gas also may go. When you say small, how much of it already? So the one which they are testing it out is in 50 megawatt range. 50 megawatt is 50 megawatt is small. I mean, it's not. So 5 to 10 megawatt is a distribution feeder. 5 of the distribution feeder connected will become like a 10. So that is a very attractive solution. So I think there are some. I read an article. I am not actively working there, so I am not looking at very closely. But I read that the waste disposal is also very clean in that small one, because it's more considered mobile, so you can move from one place to the other. So I personally think that that's going to pick up, because that's one of the challenges, right? Nuclear waste, and it's as good as problem with fossil fuel, right? Safety and these other things. So if it's safe, that will pick up. So those two technologies are already there. So, and then offshore wind or some kind of wind will be there for sure. So I don't think you will be getting rid of rotating machines. It's just going to be there. You will be probably retrofitting rotating machines, and so all the concept that we've learned in electric machines, you don't have to get rid of that course. You still need that course. I mean, otherwise it's a danger there, right? I mean, you're going from the technology, you may not even, and those knowledge is super critical, super important for fundamentals in electrical engineering, if you look at it that way. But anyway, so I wanted to touch base on how this is done at the inverter level. So, and there are comparisons which you can do. Yeah, so if you want to look at the droop, you can do these two droop, and then you can do the swing equation also connected with that. So it's a group connected with the swing equation directly, and then generating the power. So one other thing which I wanted to talk about is, we don't have time. We at least need 30 minutes for the work in here. One other thing which I wanted to talk about is the hierarchy. So we in our lab developed a method for controlling the inverter, which we call it unified, which is which can be done following and forming depending upon the operation of the inverter, and you don't have to change any control architecture. So that is done using unbalanced operation for distribution system, using an architecture utilizing a sequence domain. So it's positive sequence, negative sequence, and zero sequence domain. So what you do is that you bring it into the DQ form or in the ABC form. From ABC, you can directly convert into plus, minus, zero. So if there is a balanced system, minus and zero will be going away, only work on positive. Now if it's an unbalanced system, it works on negative and zero. So I think one of the interest that you had yesterday, you were asking about, can I have a single phase inverter working as a grid forming architecture? So single phase inverter doesn't have the concept of grid forming architecture, because in order to form the grid, you need to have to convert into DQ. For that you need A, B and C, and A, B and C is only coming from three phase. If you have one A, one inverter, another A, B inverter, how do you get A, B and C? However, if you are working on sequence combination, you have to know the fundamental sequence. That's a challenge, because if you look at an A phase, now my A phase is unbalanced. So A phase has positive, negative, zero. B is also unbalanced. You have positive, negative, zero. So generating that in a sequence representation is a little bit better as opposed to ABC to DQ. So single phase inverter. So we did some work, and I think I told you, you can actually contact me. I'll share one of my students' dissertation. It's very the first entry for us. We are also learning how you do it, but at least you'll get some small things which we did from that dissertation. So single phase concept, and also you may ask the question, do I need to go to single phase to make all the inverter grid forming? You don't have to. You can let all the single phase one follow me, and I'm in the three phase sitting there and I'm forming. That's good. So the concept is very you have to be. So when you do on research, there is another element what all students look into, at least in our world. We also want to mention something which is worthwhile and that catch attention. So don't catch attention too much and not make it not worthwhile. So you have to have a combination of that. So yeah. So I don't know whether, we worked on it in a dissertation. Like I said, it's coming out. But I don't know whether single phase inverter in forming mode is really required. It's just something which it. But the positive negative zero sequence combinations which you can utilize. The good news of this is, and now we don't have time to talk about that, but if you are having abnormal operation on the grid, which is faults, for example, one of the good news about synchronous generator is what we call it fault contribution. Have you heard of the word fault contribution? If you have a fault, what will the fault do? If you have a short circuit, if you have a line falling on the tree, what happens? It is going to draw current, okay, and we call it fault current. So the fault current is drawn by the fault, which means the nearby voltages which is giving this current start dipping. And if it is a fault which is bolted on the bus, I think we talked a little bit about bus fault, and if fault bolted on, this voltage will completely collapse, right? You know what a synchronous generator do? Synchronous generator will hold this fault current because of the inductor sitting there and the winding sitting there. It's not going to release the current. All the current which has been drawn from this winding because of the storage capability, it stores in the winding and then releases a little bit later. So the fault current is not very high shooting up. That is called fault contribution. Fault contribution meaning you are contributing towards the fault to limit the fault and maintain the current by this metal winding. Okay? The bad news of the inverter is that there is no winding, which means you are not able to contribute towards the fault. So fault contribution for the inverter is basically very less, or the fault current that can be drawn. Another property of the synchronous machine, if the current goes high, it is going out from the synchronous generator for some period of time. Synchronous generator is not going to die. It is going to like 6 times, 8 times, because it's a property of the machine. Surge, current which we have, inrush current which we call it, is coming from the machine. That is not there in inverter. So inverter, short circuit current we call it, is almost the same as a load current, which is 1, 1.1, 1.2, maximum go to 1. Momentarily some of the inverters they have tested it saying that it can go up to 1.7 or 1.8. That's it. Not 2, not 3 or not 4. So how do you manage? So that's bad news, right? That you cannot manage because nothing can be done. But let's assume this fault is not very heavy. It is unbalanced or face-to-face fault, face-to-ground. Most of the faults, 80% of the faults like that, not bolted fault. At that time, there will be current which is unbalanced flowing through very high. So this inverter can contribute towards that current, which is unbalanced current. And that is what is known as negative sequence current injection from the inverter, because all the unbalance goes to negative sequence component. Okay, the current that is going to the ground, for example, which is considered as zero sequence or whatever the current which is there, but the unbalanced nature of the current which goes to negative sequence. So with the same capacity of the inverter, what I can do? I can do a trick. I can try to reduce the active power flowing from the inverter and use this to generate reactive current and contribute towards negative sequence. Wonderful idea, but there's a catch. I need to know what is my negative sequence component. So this sequence representation will help you understand that too. Because if you are not in a normal operating condition, it will be able to generate, it will see negative sequence because you are doing sequence extraction. So, this one we did try. There is a paper in here. There is a very light version of this paper in a magazine, which is a readable version. You can do IEEE Electrification magazine. I think it's the last, one of the issue. So issues right here, and you can really do the conceptual level understand, not the math. There's no math involved in that level. But anyway, so you have this control architecture designed. This is another part that I am not able to discuss today, but the inverter, when the inverter capacity reaches, you have to limit the current flowing out from the inverter, otherwise inverter will blow. The problem with the inverter, so I cannot like even short time. At that time, you will need to limit the current, and there are ways to limit the current by looking at the power current coming out from the inverter. When you limit the current, there is a challenge. The inverter you consider as voltage source. As soon as you limit the current, it is no longer a voltage source. Right? So you are drawing the current, and you limit the current which is drawn. Then the voltage will start, it's not working as a voltage source. So all these voltage source representation, really that box is inverter, it's not, you have to change. So there are some challenges associated with that. So this is basically current limiting. So this design can work in grid connected mode, we call it type 0, can connect in non-grid connected mode, which is type 1. The grid connected mode, it is a negative sequence you inject, but it is going to take care of, another good story about negative sequence. This negative sequence component, when you extract it, even in normal operation, is good. Because suppose you have a normal operating condition, you have harmonics content, which is sitting there on the normal operating condition. This ripple and the harmonic context is generally can be represented in the form of a negative sequence. So if you push negative sequence current, you can actually take care of the harmonic content as well. Without, to some level, you still probably obviously need filters to take care of the harmonics, in uniform, but you can actually improve the harmonics as well. So this is tested some case studies tested in the field too. So this is how we, so there's no negative sequence injection in a normal operation, but for our the work the method that we have, it gives negative sequence. So because it gives negative sequence, you see the voltage balancing, except for one point, the voltage is limited. It's not shooting high. So these are some of the. Oh, anytime when you work on inverter, looking at the inverter side, what did I tell you? Like waveform. You don't do any other things other than. So now you can see some. This is a right through fault. Right through is another thing that is mandated by the grid code, which is 1547. So you can do fault right through capability. It's an unbalanced fault with fault resistance 1 ohms, and you are looking at how much the right through capability has for the inverters and how the current and voltage waveform varies. And this is actually changing from following to farming. So it is no following and farming in here, and the inverter modes can be changed. So in here we are talking about what's a delay, whether the controller works. So this inverter combination is what we see here. So I wanted to talk about this, and then I will close it. So this inverter, what you see right here is this sitting here. The control that controls the inverter is one DER is primary control, right? So if you have many of them in an electric distribution network, for example, you will need the secondary control to maintain the voltage and the frequency, right? Remember the voltage and the angle that is generated from the inverter. Where is that voltage? Where is the inverter looking at that voltage? On the point of common coupling. Can the inverter receive voltage on the substation or some other place? No, we'll see. Is that the job of the inverter controller to see somewhere else? The primary control on the inverter, if you go to inverter manufacturer, say, why from the inverter manufacturer? I don't care about what you have. I was told to just look at where I am connecting. I am delivering my goods. I can promise that voltage is high. But that voltage may not be, you may have to correct it. So that is why we said yesterday we talked about secondary controller or the other controller, which is done through optimal control. Remember that some other controller. So you can do secondary control architecture connected, which is done through signal sending from wireless, and then point of info. So I told you the difference between PCC, point of common coupling, where the inverter is connected. I told you that is not point of interconnection. Point of interconnection is bunch of the inverter connected to the point where the electric utility grid starts. It's point of interconnection. So you can actually have a global measurement, and then you can have a local V, and then you can control using the secondary control. So this secondary controller, what we observed is that if you do the droop control, the voltage on the droop control, so this is a droop. By the way, in the another thing which I wanted to, in the electric distribution system, P is not related to omega. In the electric distribution system, P is related to V. Okay, that is because the impedance of the electric distribution is at a very high resistance and low, reactance. Because of the resistance reactance, what we call it is a resistance reactance ratio, R by X or X by R. You don't know, you might have heard this term. The relationship between this droop changes. That's one of the drawback of the droop. Why it is drawback? Because if you are buying an inverter and you want to connect anywhere, you cannot connect it anywhere. You have to change it. Otherwise, it's not going to work. So in here, what I'm talking about is PV droop. So you see the power when it pushes, the voltage is going down. You see, when the voltage goes down, when the power goes from here to here, voltage goes down. You have to lift that voltage. That is done by the secondary action or secondary control action. So you have a term, an integral term that goes into secondary control action, and you can actually control the output. So maybe I'll stop right here. So today I tried to go deep into the inverter, not go inside fully in the inverter, and then talk about only the control part of the inverter, keeping the topology and other considerations of the power electronics one. not changing generic, only the control part, because that control part is related to how that is working with the grid. Also keeping on the DC side constant, knowing that the DC side dynamics are not taken care of. With that, only talked about this control and explained how that controller links with other controller we talked until yesterday. For this workshop, we cannot focus on the DC side and the inverter converter dynamics and how the other type of architecture like fact devices and all connected to the grid. So this is very active. You understand this area. It's fun. A lot of things which we can do. But the goal is basically to only connect. So in the controller, if you want to take 1 minute to refresh, in the controller, we say that the inverter is the front end. Inverter is connected to the grid. Inverter connects to the grid through this controller. And to connect to the grid and deliver what grid is required, if the grid is available, inverter needs the frequency of the grid and the angle that is working from the grid and the power that grid wants to deliver. These are only three you need. So this is done by extracting the angle from the frequency through a method called PLL. Not worried about voltage magnitude. Why? Because the grid is there and grid is connected. So the voltage magnitude is there, right? Not worried about voltage magnitude. You need to control the voltage magnitude, but not worried about developing the voltage because it is already there. And you take the power, active power and reactive power, convert that into second loop, which is basically you can call it voltage control loop, then convert that into current loop, and then utilizing that current loop to deliver the switching pulse or sine PWM signal to the inverter. Inverter as a box will work just like that. Whatever the waveform it comes into it generates the pulse, it generates the pulse, and then switches operate based on that. And then you track the output. This is the architecture for the control. That such controller is connecting and taking the angle from the grid is called grid following, because it's following the grid. If the grid is not there, that control architecture has to be switched or either changed to track the voltage and the angle, and that is called grid forming. And it is done through three different methods. One is called group, second is called virtual synchronous generator, third is called the oscillator technique. And just give a storyboard of each one of those methods. Then finally, I told you an architecture which is called unified, which means not following on forming or works in both conditions, connected to the electric distribution system, which can be run for unbalanced case as well for positive negative zero sequence. And finally, I told you how this inverter control can be linked with the other controller, secondary control and the tertiary control, which we talked about yesterday. Where at that time we said inverter is just a red dot called DER, and then we talked about grid. Now we go inside the red dot and how this dot works. So I think that concludes the overall box. We are scoping it because we cannot do more than this in 5 days. So I hope you enjoyed the discussion. It was great interacting with you all. We will have another 15 minutes only. We have, I guess, 11 o'clock. We have to start the test is what they are saying, but 15 minutes. If you want to close on your assignment that we gave you yesterday, we have time to do that. Or you have time to do something else. I don't know. I think you need to have to do that assignment. That's what my instruction from Dr. Tiwari to until 11 o'clock. So you have some time to do that. At 11, we will start the test. Okay, 11 to 11:30 is the test. Test consists of 20 multiple choice questions that you have to check. 20 questions. That is from 11 to 11:30, and from 11:30 to 12 we will be grading, and 12 to 1 will be closing ceremony. At that time we will be giving you the I think maybe certificates or closing, whatever it is on that. So that's the plan. So up to 11 you have time. Again, great interacting with you all. If you have any questions or suggestions or anything that you wanted to convey, now I am in the email list that communicating right in the loop. Please keep me posted if you need anything. Let me know. Questions?